Welcome to the lecture series on electromagnetic field theory. This is lecture number 2, generalized current concept. In this lecture we are going to cover these many topics: conduction current, which is related to free charge or the conductor; displacement current, which is related to the bound charge, which is present in dielectric material or magnetic core; impressed current, which is also known as the source current; total current, and few gate level MCQs. So these three terms has been written together because they are interrelated to each other. Similarly, displacement current, bound charge, dielectric material and magnetic core are also interrelated to each other. That is why they have been written together. So let us start this lecture. So according to Ampere's law for electrostatics, we all know that curl of a magnetic field is equal to the conduction current J, which is fine as far as the electrostatics is concerned. But the moment when electric field or magnetic field starts to change as a function of time, that means the fields are no more static, they are varying with respect to time, then in that case Maxwell noted that this particular expression is incomplete. So for time varying fields or time harmonic fields, Maxwell says that Maxwell introduced another current which is called electric displacement current, which is given by delta D over delta T. And he visualized this displacement current as a motion of bound charge. We all know that in a conductor, free charges are present, free electrons, which constitute towards the conduction current Jc. But in a dielectric, let me choose another color. But in a dielectric, bound charges are present, that is plus and minus together. These bound charges move in the vicinity of electric field. That is, when the electric field changes with respect to time, then these bound charges tend to move. And Maxwell noticed that this motion of bound charge in dielectric material, and he named it as displacement current, or precisely electric displacement current. So the motion of bound charge in dielectric constitute JD, that is displacement current. Since the Maxwell's equations are symmetric, therefore magnetic displacement current will be delta B over delta T. Now the source current, let us denote it by Ji and Mi, where this I in the superscript represents I of the impressed current. So whatever source we apply on a circuit, that we can call it as a source current or impressed current, denoted by Ji or Mi. Therefore the total current will be the summation of Ji, Jc and Jd. So if you see this circuit, there is an electric source Ji and there is conduction current Jc. This is electric source, so Ji is, this is source current. This is conduction current. And this is displacement current or electric displacement current. So this is electric source current, this is electric conduction current, and this is electric displacement current. This conduction current is due to the presence of free electrons in the conductor, which is the wire in this case. And this electric displacement current JD is due to the presence of bound charges inside the dielectric, which is present in between this capacitor. So this is capacitor C, this is the resistor R. So the total current JT is equals to delta D over delta T plus JC plus JI. Okay, so this delta D over delta T is JD plus JC plus JI. This should be JI. Okay, all right. Now let's look at this magnetic core. So this is a magnetic core, and this is a magnetic source. Now one thing which you should notice is that the magnetic sources are represented with a double arrow, which is as shown here or here, whereas in a electric source it is represented by a single arrow here or here. Okay, all right. So here the magnetic source is Mi and the magnetic displacement current is denoted by Md. So the total current M total is equals to delta B over delta T plus Mi or Md plus Mi. Okay, all right. So now look at these equations. So the total current JT is equals to delta D over delta T plus JC plus JI, and total current MT is equals to delta B over delta T plus Mi. Since these are field quantities, therefore we can say this is in field form. So total current represented in field form. Now in the previous lecture, in lecture number 1, we have seen the relationship between the between the circuit quantity and the field quantities. So if you take surface integration on one of these equations, let us say surface integration of J total dot ds is equals to d over dt, surface integration of d dot ds plus surface integration of jc plus surface integration of ji. Actually there should be dot ds also present here, dot ds plus surface integration of ji dot ds. So to the left hand side becomes I total is equals to d over dt. This surface integration of d dot ds, surface integration of d dot ds is electric flux psi plus surface integration of j dot ds will be ic conduction current I plus ii, which is the source current, which is written over here. Similarly, you can also get the total magnetic current, which is kt is equal to d psi by dt plus ki. Hence we can call these two equations as written in circuit form. Now from Maxwell's equation, we know that del cross E is equals to minus delta B over delta T. So if you add the source current Mi, then you can write this total expression as MT, which we have already seen over here. This particular expression is equals to MT, the total magnetic current. Similarly, from Maxwell's equation, we know that del cross H is equals to delta D over delta T plus JC plus JI, where JI is the impulsed or the source current. Therefore, the total current becomes JT. Hence, the Maxwell's equation in differential form in terms of field quantities is written as del cross E is equals to minus MT, del cross H is equals to JT. In integral form or in mixed form, it can be written as closed surface integration of E dot dl is equals to minus KT, and closed surface integration of H dot dl is equals to IT, which is obtained by applying the Stokes theorem. These derivations has been done in lecture number 1. If you want, you can check that. Similarly, it can also be written in purely circuit form, where these quantities V, K, I and U is in terms of circuit quantities. Hence, this represent the Maxwell's equation in circuit form. Now, if you take these two equations, so I am writing these two equations again over here, and if I take divergence on both sides, so I have taken divergence on the left hand side as well as on the right hand side. Here also divergence on the left hand side and divergence on the right hand side. Now from the vector identity, we know that divergence of a curl of any vector is 0, which is divergence of a curl of any vector is 0, DC is 0. And we also know that the curl of a gradient of any vector is also equals to 0, that is gradient of a curl is 0. This is the vector identity which we know from vector concepts. So if you see in the left hand side, we have a divergence of a curl of electric field. So the left hand side should vanish. Therefore, we can write that this divergence del dot M total and the divergence del dot J total is equals to 0, which is written right over here. And now if we apply the divergence theorem, you can get the closed surface integration of M total dot ds is equals to 0, and the closed surface integration of J total dot ds is also equals to 0. Okay, so these equations, what do they tell? It actually tells us that the lines of total current have no beginning or end, but must be continuous, or in other words, the total currents are solenoidal. As we know from the vector concepts, that whenever divergence of a vector A is 0, we call it solenoidal, or a curl of any vector, if that is 0, we call it irrotational. So in this case, we have got the divergence of the total current MT and the divergence of a total current JT is 0. Therefore, we are calling that the total currents are solenoidal. This statement is also very important, which is to be known that lines of total current have no beginning or end, but must be continuous. Alright, now I have one question for you. It says that consider a circuit shown in figure below. So this is the same circuit which we have seen above. If the rate of change of electric flux density is 5 millicoulomb per meter square second, then determine the source current Ji, given that the conduction current density is 1 milliampere per meter square and magnetic field H is equals to 7 into 10 to the power minus 3 times y ax cap plus 2x ay cap ampere per meter. Okay, all right. Now let's start the derivation. Let's start the solution. So before starting the solution, I want to tell you something, that here the rate of change of electric flux density is given as 5 millicoulomb per meter square times second. So coulomb per second is actually nothing but ampere. So this can also be written as 5 milliampere per meter square. That means this is a current density, or we can say that this is electric current density. Since it is rate of change of electric flux density, that's why it is electric displacement current density. Okay, now let's start the solution. Since we know that del cross H is equals to JD plus JC plus JI, which is equals to JT. In the question, it has been given that the rate of change of electric flux density, that is JD, is 5 milliampere per meter square. And it is also given that the conduction current density JC is equals to 1 milliampere per meter square. You have been asked to find JI. You don't know JT yet. So you have to find JI. You don't know JT, but in the question it has been given that the magnetic field H follows this relation. So if someone knows how to find out the curl of a magnetic field, then the job is done. So here the del cross H is equals to AX, AY, AZ, del by del X, del by del Y, del by del Z, HX, HY, HZ. So in the question, if we see carefully, that magnetic field H has a X component and also has a Y component, but the Z component of magnetic field is absent. So HZ is 0. Now if you solve this, you will get AX times this minus AY times this plus AZ times this. Okay, that is AX times del Y by del X of HZ, that is this multiplied AX times del HZ by del Y minus del HZ by del Z, negative AY cap del HZ by del X minus del HX by del Z plus AZ cap del HY by del X minus del HX by del Y. So it is just the curl operation on magnetic field. Now this del X by del Z is 0, del Y by del Z is also 0, del X by del X cancel out, becomes 1, and del Y by del Y also cancels out, becomes 1. So only AZ component remains, only AZ components, which is equals to AZ 2 minus 1, which is 2, this is AZ times 2 minus 1, which is written over here. Now since in the question this magnitude was also present, so I am multiplying this here. So we can tell that this is del cross H, which is equals to J total. So the total current density is 7 milliampere per meter square. And you can also tell that the direction of the total current is along Z direction, because the AZ cap component remains. So J total is equals to 7 milliampere per meter square. Now we know that JT is equals to delta D over delta T plus JC plus JI. So Ji becomes 1 milliampere per meter square. So it has been asked to determine the source current Ji. So the answer is 1 milliampere per meter square. Now finally, I have two questions for you. The first question is, the total current in a circuit is irrotational, solenoidal, both A and B, none of the above. Second question says, consider the following statements. The motion of bound charges in electric material constitutes electric displacement current. Second statement, lines of total current have no beginning or end but must be continuous. This is third. This should be okay. So this is third statement, which is isolated magnetic current do not exist. So you have to tell which of the following statements are correct. So only one is correct, only 1 and 2 are correct, only 2 and 3 are correct, or all the statements are correct, or all are incorrect. So if you have understood this lecture, you should be able to answer these two questions, and I hope that you have understood this numerical type question, which was important in terms of gate level complexity, and these two questions will give you a certain amount of confidence that you know how the generalized current concept works in case of time varying electromagnetic fields. So please write down in the comment section what are the answers for these two questions, question 1 and question 2. Also justify why you have selected a particular option. I hope you have gained some knowledge from this lecture. If you have any doubts, please write it in the comment box. Thank you.